All right, so let's start the afternoon session. The first speaker is Bhaskar, and he'll tell us about light-dark sectors and how to look for them.
Thank you, and let me first thank the organizers for inviting me to give this talk, and lovely setting, many discussions, and quite a few new ideas. I hope they would be converted into some exciting results at some point. Okay, so the title says inelastic exploration. So what I will do, I look for light-dark matter like a sub-GeV in the neutrino experiments, and where the signal would be line signal. And right from the beginning, you may think that this is counterintuitive, at least based on Louis' talk in the morning, because neutrino flow is a problem. But it's kind of, I'm diving into the kind of a neutrino ocean or whatever, and to extract dark matter signal. And but let me give you the truth that at the end you will see that you'll have like a much better dark matter sensitivity in these neutrino experiments, beam dump or large neutrino detectors. And if you are still awake till the end of my talk, I'm awake because so much of food, good food. But after 30 minutes, I hope you'd be able to appreciate the beauty that it really works that way. Okay, so one thing. These dark sector models would have these light mediators, which I'll be playing with, light mediators, sub-GeV dark matter, and try to explore them at the neutrino experiments. And these models also have the ability to kind of provide an explanation for the mini-boon anomaly. But I won't get into that. I'll just allude to the mini-boon anomaly explanation, since after all, this week is the focus of this week is some anomaly exploration, and Georgia's talk kind of started the whole week that way. Okay, so now the scales of new physics, they can be anywhere and everywhere, and the question is where is the scale, and which experiments would find it? Nobody knows, but there are many attempts. You can see direct, indirect detections, Large Hadron Collider, neutrino experiments, beam dump experiments. All of these experiments are searching for new physics scale. And LHC is excellent in terms of searching the scale at greater than 1 GeV. But in this talk, my investigation would be scales below a GeV, and this scale is good in addressing all the existing anomalies, puzzles like a origin of dark matter, neutrino masses, anomalies like mini-boon, G-2, etc., etc. And also, this sub-GeV has kind of different kinds of light mediators, dark matter, and there are lots of model building activities. And in this talk, what I'll do, I'll give a couple of examples, coming from two different directions of this sub-GeV models, and then I will utilize them to search for light dark matter using the ambient and laboratory sources. So model one is a T3R extension. T3R just is a quantum number associated with the right-handed quarks and leptons. A lepton and this neutrino is extra. And this is an anomaly-free quantum number assignment, and the phi is the scalar field which breaks this E1 local gauge symmetry E1 spontaneously, and we choose the E1 breaking scale to be 1 to 10 GeV. And this model is introduced to address the mass hierarchy of these fermions in the standard model, where you see like a 0.5 MeV to all the way to hundreds of GeV, 100 GeV, 170 GeV, the top mass. And So also in this model, you can have this dark matter candidate, which comes as a combination of eta L and eta R, and U1T3R breaks down to some Z2 symmetry at the end, and the dark matter is parity odd, and also eta L and eta R can have Majorana and Dirac mass. So at the end, you can have a pseudo Dirac dark matter with a small mass splitting. So, if you want to deal with inelastic dark matter, that's also a possibility here, but I won't deal with that. And so the Lagrangian, you can see that this is the standard model Higgs, and then the phi new field, and the lambda, this is the coupling, and this is the some like high scale. And so this combination takes care of your mass hierarchy, and phi wave is about 1 to 10 GeV, and lambdas in this case you need 0.1 to 1 instead of this very small lambda values which you need in the standard model. Also, this I've written it in the form of non-renormalizable operator, but it can have a renormalizable beginning. Like you can have this vector like quarks. Basically, it's a story of universal seesaw. If you stick in that universal seesaw here, then easily you can get this kind of non-renormalizable operator after you integrate out this heavy field. So now, once you fix the vacuum expectation value of the phi and the mass of the A prime, you fix all the couplings, and the couplings of phi's are with the quarks, leptons, and all this stuff. And also the anomaly can be cancelled. Among these right-handed elements of this standard model, from first generation or across the generation or the second generation. So you have many possibilities there. And for example, if you use the first generation right-handed quarks and this right-handed muon, and then nu r is the new neutrino, and then you can get a parameter space like this in the M5 versus MA. And so this more, you can see that there are lots of white spaces which can be which are still allowed. And with the combination of phi and A, you can satisfy this G-2. And also, the one interesting thing that happens once you have this scalar as well as vector, you have both P wave and S wave. And usually, if you just the A prime, then you have the problem of CMB, and you need a small mass splitting of this dark matter. But here you don't need it, because if your P wave dominates, then of course its velocity suppressed down. So it's naturally this model would be fine with the CMB constant. So, but similar models can be constructed with L mu minus L tau, BEL, just spontaneously broken symmetries, and then you can add a phi. So the interesting thing about this model is that you not only have a light A prime, but also you have a light scalar, and as well as dark matter. So this is one setup model. So there could be another setup model, for example, which can come by extending the Higgs sector by, like a standard model Higgs sector, just add doublet, triplet, or a singlet, you don't need all of them, but some combination. And then you minimize the Higgs potential and figure out the mass spectrum of that model. And you'd see that if you try to do that calculation, then it's not difficult to find a sub-GeV mass for the lightest particle, and the heavy mass to be about TeV order. So that's not a huge hierarchy. And so it's possible to build that kind of little bit hierarchical spectrum in the context of this extended Higgs sector. So and in this case, of course, there is no A prime, but you can have a that light scalar as well as your, now the model is kind of based on this U-core couplings only. So you can have, suppose, new type of some sterile neutrinos you can bring in, and the new couplings and all this stuff. So these models also can be versatile in terms of like a NSI. If you want to construct light mediator-based NSIs, you can do that. And also you can have this sterile neutrinos and many such possibilities. So that means for light scalar, or light mediator scalar or vector type, you can have plenty of model possibilities, and I just showed two, but you can have your favorite model, and you can have new ideas in terms of building these models. So now, as I said, these models explain this G-2 mini boon. So for example, model 2, the extended Higgs sector can, can explain the mini boon with a, if you include a sterile neutrino through upscattering. And on the other hand, model 1 with a gauge boson and a scalar combination, it can explain the mini boon anomaly without requiring any neutrino, just purely the dark sector. And actually, this is probably the only example where people have shown that. Or we have shown that it's possible to explain the mini boon anomaly. And the idea is very simple. You use the charge pion or kaon to produce these light mediators, and the light mediators come to the detector, and they scatter. In that scattering process is kind of an inverse Primakov and produces just a photon. And 1 photon plus 0 proton is the signal. But only on the other hand, if you go through dark matter, there could be an upscattering, or sterile neutrino could be an upscattering. But these situations are not upscattering. Is just a straightforward scattering and producing 1 photon and a 0 proton. And so this scenario does not come with E plus E minus. So if at the end Georgia gives us that little bit of excess in that channel, then it could be very interesting for this kind of scenario. So, and again, as I said, you don't need any neutrinos to come up with the anomalies. But one thing you need to make sure that you explain you explain the energy, observed energy spectra, and this cosine spectra of this anomaly, and the cosine spectra is especially interesting because it's forward, but not too forward. So, and one can address that. For example, this exchange particle could be a pi naught V gamma, and all this stuff. So we had a fit to this data to this puzzle, and we have some prediction for microboon, SBND, etc. But anyway, so both models, for this talk, what I'll do, I will use these models like a phi prime, A prime, and then light dark matter, and light dark matter is available in both models. And what we'll do, we'll explore this dark matter at the neutrino experiments. And so first, the way to do it is to produce this light dark matter. And if you are in the beam-based experiment, and then that light mediator decays into dark matter pair, and dark matter pair those dark matter particles come to the detectors, and then they produce some scattering signal, and we'll use the coherent or the 1 GeV based the proton beam based experiment, because they have the largest POT, and also light mediator would decay. It does not need to survive till the detector because it's a dark matter, and so it can decay anywhere, and the dark matter can come to the detector. And so in that case, the distance between the detector and the target, if it is small, then it's always beneficial. And then also I'll try to explore these scenarios in the large neutrino detector like Juno, Borexino, Dune, and Hyper K, and we will see some interesting result there as well. And so, as I said, neutrino experiments, I will utilize the neutrino experiments to produce these mediators. And the way it happens is, in beam dump-based experiments, proton hit the target, and you produce all these particles like photons, electrons, pions, kaons, and charge pions, neutral pions, and all this stuff. And so there are a variety, 800 MeV to 3 GeV. You have coherent CCM, JSNS square ongoing, and there are a variety of detectors. as Louis mentioned, and then also this SBN program, which is also ongoing. So, like also there are, but at the SBN program, the beam energy is higher. But here for this CCM coherent, their POT is higher and the detectors are much closer. So for dark matter searches, it's better to use those GeV based and the situation where the detectors are closer to the target. And now these particles, what it does when it gets produced at the target, they produce these light mediators, Primakov, Compton, associated production, resonance, Bremsstrahlung. So there are a variety of ways. And also, it can come from the charged pion, I think Shodong mentioned, and also neutral pion. And charged pion could be bigger in the contribution could be bigger in the case of when you have magnets focusing them compared to the neutral pion. And then, there are a variety of ways in this way. And also, one cannot forget the proton Bremsstrahlung or this parton production, but parton productions are a little bit at a higher energy. And also there could be some innovative ways one can produce these particles. And we would use mostly the nuclear de-excitation at the detector, but also one can use them at the target to produce these things. Also, neutrons can be used because there are protons hit the target, produce lots of neutrons, and they can brem off and then produce light mediators. So there are a variety of ways you can produce these light mediators in these places. And as I said, these light mediators then produce this dark matter. Dark matter comes to the detector, produce the scattering. And here is an example of nuclear recoil, but there could be electron recoil. So various ways, and low threshold detectors, of course, would be useful. And in this case, as I said, 10 to the power 23 proton, for example, if you take the example of coherent, and you can have about 10 to the power 21 pions there, or 10 to the power 21 to 10 to the power 22 pions, and then about 10 to the power 6 dark matter, or 10 to the power 16 dark matter particles can be produced depending on the coupling. And so there are a lot more dark matter particles, so you can really investigate the parameter space with a lot of sensitivities. But there is a problem. The problem is, neutrinos are also there. So, the neutrino floor. So how to kind of get rid of the neutrinos for this beam dump based experiment and then try to find the dark matter. So now for this experiment, there is an interesting thing. The neutrinos emerge from the prompt decays of the pion to muon mu, and also the decay delayed. So prompt is like a 10 nanosecond and delayed is microsecond. So that means if you keep your measurement within like a less than the lifetime of the muon, then you would be dealing with only the prompt neutrinos. And also, the interesting thing about the prompt neutrinos is their energy is kind of a 30 MeV. That's the mass difference between pion and muon. So that means that would produce up to 10 or 11 keV of nuclear recoil. So if you want to use the dark matter particle with a nuclear recoil, or dark matter with nuclear recoil greater than 10 to 11 keV, then you kind of deal with no neutrinos. So neutrino backgrounds are completely gone. And since coherent already has seen coherent elastic neutrino nuclear scattering events at 11.6 sigma, cesium iodide, liquid argon, germanium. So one can use that experiment to investigate the dark matter parameter space. So, but this is the story for elastic scattering, but I'm just setting the stage to appreciate first the elastic scattering, and then I will turn on the inelastic probe, and you will see that you will do better than the elastic scattering. So this is just the story what I mentioned. Like you confine yourself to recoil energy greater than the 13 keV or so, and then timing wise you should be within the 2 microsecond. And once you do that, you can remove the background, and actually you can remove also the NSI neutrino if there is an NSI being present. So one would do the same thing for CCM and JSNA square, and actually this timing measurement becomes possible because this beam say coherent CCM JSN square they are using, they are pulsed beam. Okay. And so this is one way to remove the neutrino background. So you don't deal with neutrino floor anymore. And there is another way one deals with it by just measuring the delayed neutrino spectrum. And from that, you try to kind of predict the prompt neutrino. If standard model is the only theory, of course, that's another way. But if NSI is there, then it's a problem. So the usually coherent uses the second method, and CCM uses the first method. The first method needs this T0 to be known very well, and T0 is the time when the proton hits the target. So, but anyway, both both estimates give similar results. So this is the elastic result. So you can see that this is the current parameter space, and more or less coherent dominates. And this is the CCM. CCM just had a couple of weeks of engineering run. Now they are doing the 3-year run. And so this pink region, so bounded by the coherent up to 10 MeV dark matter mass, and below that, it's given by this LSND or the mini boon, those constraints. And there actually you look for this electron recoil. And for coherent CCM, these are nuclear recoil, and those are for the nuclear electron recoil. So if you look for this hadronic dark matter coupled to a mediator which talks to the quark only, then you'd see that though that pink region is totally gone, all you are left with this coherent constraint, and coherent is the leader in this case. And this flattening is happening because of the threshold, because you need the transferred momentum or transferred energy to be above certain value, so that so you can get that nuclear recoil. So any mass of A prime below that would, this experiment would be insensitive. So that's why more or less it becomes flat. So now let's turn on this inelastic nuclear scattering. So like the same process, A prime hits this N, and N goes to N star. N star is the excited state. And then what happens, this excited nucleus then de-excites and produce this photon. And so in this case, only photon energy you get of the order of 10 MeV or so, depending on the detector material. And so, but this calculation is a little bit on the kind of trickier and more intensive side, because it's a nuclear physics, and lots of calculational uncertainties that are there. And then we use this shell model code, and so to handle this complication. But before that, what you need to do, you need to write this cross section in terms of these multiples, multiple moments, and you can see that there are lots of these moments that would contribute. But interestingly, when you do the calculation or when you try to estimate, then you'll see that the dominant contribution comes from this T electric component, which is actually associated with the Gamow-Taylor transition. And actually Gamow-Taylor transition dominates, and which is very good for the purpose of this calculation, because if you keep all the terms, it takes a lot of time. But if you just keep the Gamow-Taylor contribution only, that more or less gives you the full contribution, or estimate the contribution quite accurately. And so here, for example, if you keep the up to 16 states or 9 states, and these are the orange line or blue line, but if you keep the Gamow-Taylor, more or less you can see for lower E recoil, it saturates the what you expect. And for these experiments, or for the CCM JSN square or coherent, mostly we are in this region where ER is all next to 0. And also Gamow-Taylor contribution survives to the long wavelength limit, or Q equals to 0, or the 0 momentum transfer limit. So, and also it's easy to calculate in any shell model calculation. And now actually the way we started this calculation, just to see how much inelastic contributes to this cross-section, elastic cross-section, and you can see that if you compare the elastic to inelastic, it's a 3 order of 1 to 3 order of magnitude down. So inelastic really gives you like 1% of the elastic cross section. So it's difficult to find that contribution if you do the cross section measurement. Like what Louis showed in the morning, and that cross section is absolutely saturated by the elastic. But inelastic comes with something else. The elastic, you look for the nuclear recoil, and then you look for this KV energy deposition. But on the other hand, the nuclear inelastic, it comes with the signal in the MEV region. So completely different region. And the background is different. Actually, background is much smaller than what you expect in the KV region. And you don't need all these acrobatics with timing, energy, and all this stuff, because anyway, neutrino background would be small. And so for this thing, like you can have different detectors like cesium iodide, sodium, argon, and all this stuff. Actually, Carmen had a very good measurement. They actually saw this 15.11 MeV carbon line, and that's based on this new mu scattering. And so that line actually can be utilized to explore the dark matter parameter space. But but on the other hand, CCM uses argon, and coherent now is running with sodium iodide, also germanium, but sodium iodide is about 3.5 ton. So we can utilize this to explore the parameter space. And this is the carbon line. Actually, they observed it. And this is the CCM measurement of the MEV region based on 2 weeks of data. Now, this background actually would be reduced, or already has been reduced by a 2 order of magnitude, almost 2 order of magnitude in the current 3-year run. So, the best thing would be if CCM observes also this de-excitation photon for argon. Neutrino induced or dark matter induced, that would be great for this Dunes supernova and the dark matter program in the long run. So now this is the parameter space, and you can see that this is the coherent solid line is the coherent elastic limit. Green is the CCM elastic limit, but Carmen is much better. Same dark matter parameter space, but I'm using this inelastic scattering. So at least you can see that more than an order of magnitude different for lower mass, but it continues to be much better even for higher masses. And this dashed line is for 100-ton liquid argon, like CCM is planning. Also, there is a Fermilab facility P2. They are also planning. So but argon line has not been observed in this experiment. But we use this this experimental result from Los Alamos to kind of address this strength calculation or normalize the strength calculation to estimate this sensitivity lines. And also you realize that these lines are not limited by this flatness, so it continues like that. And so if you go to this alpha B parameter space where you see it a little bit better because you don't have those pink region or this electron recoil regions, it's purely nuclear recoil, and you compare that with the inelastic channel, and you can see that clearly that nuclear de-excitation is much better. So now I turn my attention to this ambient dark matter, because this is kind of a lab-produced dark matter. So for the ambient dark matter, of course, if you want to produce this de-excitation photon, you need some energy, or the dark matter needs some boosting, and that boosting can come from the cosmic ray scattering. And in this case, same hadronic interaction of dark matter via this mediator also make it to interact with the cosmic ray particles. And this is the elastic scattering. So for the dark matter parameter space for light mediators. So once we probe them, now what I'll do, I'll just probe the same thing with the inelastic scattering, and I'll do it for hyper K, Dune, Juno, Borexino. And Borexino already has data, but they have not made the line measurement. So we're suggesting them to go for it. And Juno is upcoming, and Dune, hyper K will be future. But one can compare all these experiments for these measurements. Also, the elastic channels as well. So this is the coupling versus parameter space point. And so this shaded region is ruled out by this elastic data at this point. And you can see that Juno at this point gives you the best sensitivity, then Dune, hyper K, super K, and it goes on. But the Juno's best sensitivity came because Carmen has observed the new mu induced de-excitation photon at 1511. But for liquid argon, we don't have such a measurement. So there are a bunch of de-excitation lines, GT lines, which we combine to estimate that and use that Los Alamos result. But if, for example, one of these experiments at coherent or CCM observes the line at liquid argon, definitely this Dune line would become much better. So at this point, Dune prediction is up to that uncertainty. So, if you compare this parameter space with the beam dump best, but beam dump best always obeys this limit that dark matter mass has to be less than 1/3 of this or 1/2 of the A prime mass. In that limit, of course, beam dump does the better job because it's you can produce more dark matter than what you can get from this atmosphere after this cosmic boosting. And this is just the cross section. This cross section is kind of put it in a heavy mediator approximation, but just to show you that what could be the how does this measurement compare with the existing limit. So you can see that it's again more than an order of magnitude in most of the parameter space. And I used like two A prime values, but one can do it for higher A prime values. But larger A prime values has a problem with the cosmic flux or cosmic boosted flux because most of the flux actually comes from like about GeV or less, and so that's why like higher values of this A prime mass would have less flux. So anyway, so let me come to the conclusion that like mediators can explain various anomalies and puzzles, and less than GeV is difficult at the LHC, and there are many beam dump based experiments where sub GeV mediators are being probed along with the sub GeV dark matter. But what we are introducing, this inelastic searches, these line measurements are a little bit cleaner because it's a line. So from the continuum background, it can be separated. And so it seems that it gives you a very good ability to probe the dark matter parameter space. But this is not the only example. So actually, one can probe atomic anomaly. And in this neutrino experiments, again, using these inelastic processes. And then also one can have this axion dark matter absorption. Suppose these are coming from reactors or beam dump, but they can be absorbed at the detectors and produce the lines. So there could be many possibilities to probe new physics using these inelastic channels. Oh, thank you.
Thank you. There's a question right there, Luis.
Yeah, regarding the mini-Boone anomaly, you said you can explain it, but Is the explanation consistent with the lack of signal at microboom?
Oh, okay. Should I answer? Okay, good. So microboons data for 1 gamma 0 proton at this point. So the data we have seen so far does not exclude this mini-boon example. It excludes a bit of parameter space, not the entire parameter space. We are eagerly waiting for the second round of data. And even with if they see a signal, that would be great. If they don't, even then there would be some parameter space would be left. SBND would be able to cover it. SBND is ongoing, and so they would be able to cover it. Correct?
And a related question is, I mean, you already mentioned the angular distribution.
Yeah.
But I mean, my personal experience is that with light mediators, it's very difficult to produce an angular distribution that is not too forward peaked compared to the
Perfect. Actually, we struggled on that. So, you know, like during that COVID time, the strugglings were from different directions. But anyway, the way to solve that puzzle is if you look at the Primakov scattering via photon is very forward. So, but as soon as you put any mass in the T channel, it starts becoming off forward.
But then you get your signal in the incoherent channel where you emit.
Good question. Now the question is up to where the coherent limit exists. Now, if you exchange a pion up to 100 to 150 MeV, it's still coherent. And so now if you can, I'm not saying you need to bring a pion. So for pi 0 V gamma is the easiest channel to bring it. And we checked the coherency in that, and mostly it's coherent. But you don't need to bring coherent. You bring a mediator of the of mass like a 70 MeV, 80 MeV, good enough. So that's the way you can solve the puzzle.
Thank you.
Mr. Pascal,
Mhm.
on page 31, on page 31, can you go back to like page 31?
Base that, you know, so
Yeah.
just a second.
So it shows
35, 34, 33.
sensitivities, compares sensitivities.
Perfect.
Oh yeah, it compares, so the Carmen is considering the inelastic scattering.
Yeah.
While, but for the case of elastic scattering, I can understand why it looks like a flat.
So actually I mentioned that, but it was probably, I did not make it clear. So it gives me an opportunity now. So for elastic scattering, there is a threshold. And if the threshold is suppose 5 keV for cesium iodide. And then the transferred momentum is Q square is 2 Mn times ER. And if Q square value is bigger than the Ma prime mass, this becomes insensitive to the
Right,
Ma prime.
that's what I understood from elastic
Right.
scattering. But why for the inelastic scattering?
Inelastic scattering, the line for carbon is at 15 MeV, which is lower than 2 times MnEr or cesium iodide, also 5 MeV line, or sodium iodide, there is a 5 MeV line. So that's the reason. So less transferred momentum is needed. So that's why it becomes more sensitive to lower values of Ma prime. Of course, at some point your luck could run out, but that's less than a MeV. Right. If I had shown you less than MeV, and then you would have seen the saturation there. Right.
Are there any more questions or comments? All right, we should thank Bhaskar again.